The topic of this lecture is confidence interval. So we will be looking for confidence interval for a normal population mean, mu. So this mu is mean value for random variable x which has normal distribution. To address this problem, let us start with something simpler. Let's consider random variable z which has standard normal distribution. And let's find value of c such that probability that absolute value of z is less than c equals to 0.95. We already addressed almost the same problem before, but it's a very important problem and I want to show you once again how to deal with this. So probability that absolute value of z is less than c is the same as probability that z is more than minus c and less than c. This equals to probability that z is less than c minus probability that z is less than minus c. And this equals to probability that z is less than c. This number is found from the table for normal distribution. And next term will be 1 minus probability that z is less than c. We discussed all of this in lecture number 21. Therefore, we'll have 2 times phi capital of c minus 1. And we want for this to be equal to 0.95. Thus, 2 times phi capital of c equals to 1 plus 0.95, 1.95, and from here phi of c is 0.975, and from here using table for normal distribution we find that c equals to 1.96. You remember about this number. I suggested you to remember this. So what we got, what this all means. Probability that the absolute value of z is less than 1.96 equals to 0.95. This means that if we take a measurement, we make measurement of z and get value of z many times, then in 95 cases out of 100 value of z will be in this range, in this interval, minus 1.96, 1.96 in 95% of cases. So although z can have any value from minus infinity to plus infinity, in 95% of cases z will be in this. Similar problems is finding c if probability for absolute value of z less than c equals, say, to 0.9. And from here we find, just using previous method, c will be equal to 1.64. And another common problem when probability is 0.99. And from here we find that c equals to 2.58 roughly. So again, if we make 100 observations, then in 99 cases out of 100, c will be between, so z will be between minus 2.58 and plus 2.58. In 9 cases out of 10, it will be z will be between minus 1.64 and 1.64. It's quite similar to what is in here. Just this number changes and this number changes. This and this. Now we extend this problem to a random variable x, which has normal distribution with mean value mu and variance sigma squared. We know that z, which equals to x minus mu divided by sigma, has standard normal distribution. And this means that probability, well, this means that z by absolute value less than c implies that x minus mu divided by sigma by absolute value less than c. Or this means that x minus mu by absolute value less than c sigma. Thus, probability that absolute value of z less than c equals to probability that absolute value of x minus mu less than c times sigma. And this particularly means that probability that x minus mu by absolute value less than 1.96 times sigma equals to 0.95. We found it before, so it is for this. If here c is 1 point, if this is 1.96, then probability should be 0.95. Now, what we got? We got same kind of observation as we had for z. In 95% of cases, random value of random variable x will be in the range from mu minus 1.96 times sigma and mu plus 1.96 times sigma. So it will be difference between x and mu is smaller than 1.96 times sigma. Now we make next extension of this problem. So we take a sample of size n for random variable x, which has normal distribution with mean value mu and variance sigma squared. Then sample mean x bar will also have normal distribution. We discussed it in lecture 22 with mean value mu and variance sigma squared divided by n. And now we can put it same way. If we extend what we know about x and z, we can put it like this. Probability that x bar minus mu by absolute value less than c times sigma divided by square root of n equals to certain probability. So if here we have 1.96, then here will be 0.95. So this change from sigma to sigma divided by square root of nu is because here variance now sigma squared divided by n, so sigma divided by square root of nu is standard deviation for sample mean x bar. And it's quite often is called standard error. Now x bar minus mu by absolute value being less than c times sigma divided by square root of n means that, let's say, mu minus x bar more than minus c times sigma divided by square root of n and less than c times sigma divided by square root of n. And from here we can make an estimate for mu if we don't know mu. So mu is bound from two sides. On one side we have x bar minus c times sigma divided by square root of n, x plus c times sigma divided by square root of n. So this means that mu appears in interval x minus c sigma divided by square root of n, x plus c sigma divided by square root of n. And this is called confidence interval. For mu. If c equals to 1.96, then this is called 95% confidence interval. If c equals to 1.64, then we have 90% confidence interval. And finally, if c is 2.58, we get 99% confidence interval. And meaning of this is following. For example, if we consider this case, so we take lots of samples. We take one sample of size n, the next sample of size n, and so on and so forth. For each of these sample, for every one, we find sample mean, and based on this sample mean, we find this confidence interval. For example, 95% confidence interval. And 95% confidence interval would mean that for 95% of samples, mu will be in this interval, but there is still 5% of samples such that mu is not bounded, doesn't appear in this confidence interval. It's not bounded by this range. We can also note that 90% confidence interval is shortest one, then 95% confidence interval is larger, and 99% confidence interval is even larger. So we should take larger interval if we want to have mu to appear on this interval more frequently. Let us find confidence intervals for the example presented here. Cholesterol levels in boys of a certain age are believed to be normally distributed with unknown mean mu and standard deviation 30. A sample of 20 boys has their cholesterols measured, and the sample mean is found to be x bar equals to 185. So if we want to find 95% confidence interval, then this is found as x bar plus minus 1.96 times sigma divided by square root of n, which is x bar is 185 plus minus 1.96 times standard deviation is 30, and n number of sample size is 20, square root of 20, and this is 185 plus minus, if we calculate this number, it will be 13.1. So this confidence interval, so 95% confidence interval, is given by this interval 171.9 and 198.1. So in 95% of cases, mu will be, values of mu will be in this range. If we can find also 90% confidence interval, the only difference is value of c, this value. So it will be x bar plus minus 1.64 times sigma divided by square root of n, which is 185 plus minus 1.64 times 30 divided by square root of 20, and this is 185 plus minus 11.0. Or this can be put it like 174.0 on one side, 196.0 on the other side. So this is 90% confidence interval. As we can see, 95% confidence interval is wider than 90% CA. 95% CA is larger than 90% CA. Let us consider a bit more difficult case. Consider random variable x, which has normal distribution with mean value mu and variance sigma squared. So what difficulty here, for example, can be like this. We know that x should have normal distribution. We don't know neither mu nor sigma squared. How in this case, how to find confidence interval for mu if sigma squared is unknown? So this can be done again using a sample. So we take a sample of size n, then find mean for sample and standard deviation S and standard deviation S for this sample. Then S, then in formula Ci x bar plus minus c times sigma divided by square root of n. Sigma can be replaced by s, but in this case we get an approximate confidence interval. What means approximate? Approximate means that if we have sigma, if we know sigma, then exactly for example, in 95% of cases, when c is 1.96, we will have mu in this range. But when we say approximate, it is about 95% of cases, but not exact. We don't know exact number here. So this is a difference. Another comment we can make here is when n is larger n, better this approximation, better approximation of the size of confidence interval. Let us find 95% confidence interval for this example. In fuel consumption tests on a particular model of car, 50 cars were each driven under identical conditions, and the distance covered on 1 liter of petrol recorded. The sample mean was calculated to be x bar equals to 10.5 kilometers, and the sample standard deviation S is 1.515 kilometers. So again, we have a sample, and for this sample we found x bar and S. An approximate 95% confidence interval is found. We know how to do it. It will be x bar plus minus 1.96 times S divided by square root of size of the sample. Size is n is 50, S is 1.515, and x bar is 10.5. So this equals to 10.5 plus minus 1.96 times 1.515 divided by square root of 50. All this equals to 10.5 plus minus 0.42, or we can put it like this, like 10.08, this in form of interval, 10.92 kilometers. Quite common problem associated with confidence intervals is evaluating of hypotheses. If someone, for example, says that mu should be equal to 10 kilometers, whether we would believe it or not, whether we can say that our data, that our confidence interval supports this hypothesis that mu equals to 10 kilometers or not. So we can't say we support it because 10 kilometers is outside of our 95% confidence interval, and this means that we reject the hypothesis that mu equals to 10 kilometers because it's outside of our confidence interval. At least we can say this at 95 confidence level. We reject this hypothesis. 99% confidence interval is given by this formula, 10.5 plus minus 2.58 times 1.515 divided by square root of 50, and this equals to 10.5 plus minus roughly 0.55, or it is an interval starting at 9.95 and that's at 11.05. Now mu equal to 10 kilometers is inside 99% confidence interval, and we conclude that we can accept the hypothesis that mu equals to 10 kilometers can be accepted at 99% confidence level. And from here we conclude that higher confidence level is weaker evidence to accept hypothesis. We remember that 90% CI is smaller than 95% CI, and therefore if we can't accept hypothesis at 90% confidence interval, we also reject There is slightly different way to evaluate hypothesis, which includes measurement of so-called p-values. To illustrate this method, I will use an example which we have already seen. So again, cholesterol levels in boys of certain age are believed to be normally distributed with unknown mean mu and standard deviation 30. A sample of 20 boys have their cholesterol measured, and the sample mean is found to be 185. So what we want to check that mu equal to 175 is supported by given observation. The difference between expected mean value 175 and measured sample mean 185 is 10. And what we want to find a probability that sample mean, that this difference between sample mean and expected mean value is more than 10. And this is called p-value. So probability that x bar minus mu is this 175 by absolute value more than 10 is probability equals to probability that x bar is more than 185 and x bar is less than 165, which is found like probability that z score of x bar is more. I will not show these calculations, I will just give results. So value in terms of z corresponding to 885 is 1.49 and value corresponding to 165 is minus 1.49. And this equals to 2 times probability that is more than 1.49, because this probability equals to this probability of these two events. And this equals to 2 times 1 minus probability that z is less than 1.49, and this is 2 times 1 minus value of phi capital, which is found from table for normal distribution, 0.49, and if you find it, you find this is equals to 0.13. Thus probability that sample mean minus mu more than observed value and expected mean value, which was hypothesized, equals to 0.1362. Thus, in 13.6% of cases, sample mean will be outside of interval 165, 185. That is, in 13.6% of cases, the difference between some sample mean and hypothesized expected mean will be larger than in this particular observation. P-value equals to 13.6%, which is, let's say, more than 5%, and therefore at 5% significance level, which corresponds to 95% confidence level. There is insufficient evidence to reject our hypothesis. If we calculate 95% confidence interval for this problem, that we will find that it is equal to 171.9, 198.1 on the other side, and 175 is inside of this confidence interval, and we don't reject the hypothesis. That mu equals to 175.